In this video we look at the work on polar coordinates required by Unit 4 of the WJEC Further Mathematics Specification. We have to be able to use polar coordinates and be able to convert between polar and Cartesian coordinates. We have to be able to sketch polar curves, and we have to be able to find the area enclosed by a polar curve. If the point P is represented by the Cartesian coordinates x, y, and also by the polar coordinates r, theta, then x and y are given by x equals r cos theta, and y is given by r sine theta. If we know the Cartesian coordinates and want to find the polar coordinates, then we've certainly got r is the square root of x squared plus y squared, because r is simply the distance of the point away from the origin. And we have tan theta is given by y divided by x. But be careful, that does not mean that theta is tan to the minus 1 of y over x. In order to sketch a polar graph of r equals a function of theta, it's worth following these steps. If there is a maximum value of r, find it. Find also the minimum possible value of r. And if this turns out to be less than 0, then for the values of theta for which r is negative, there are going to be no points on the curve, because our curves are only defined if r is greater than or equal to 0. If we solve the equation r equals 0 and find that theta equals alpha is a root of this equation, then the ray theta equals alpha is a tangent to the curve at the pole. If r is a polynomial or rational function of cos theta, then the graph will be symmetrical about the initial line, that is the x-axis or the line theta equals 0. On the other hand, if r is a polynomial or rational function of sine theta, then the graph will be symmetric about the line theta equals plus or minus a half pi, in other words the y-axis. If we wish to find the point of intersection of the polar curves r1 equals f of theta and r2 equals g of theta, then there are two things we need to do. First of all, we can find the solutions of the equation f of theta equals g of theta, and solutions to that equation will give us all the points of intersection except the pole, the point where r equals 0. And we then need separately to consider whether the two curves both go through the pole. If they do both go through the pole, then we need to say the pole is also a point of intersection. Solving the equation f of theta equals g of theta will not generally give us all of the points of intersection. It will lose the pole. The tangent to a polar curve will be parallel to the initial line if dy by d theta equals 0, where y equals r sine theta, which is the same thing as f of theta times sine theta. On the other hand, the tangent to the curve will be perpendicular to the initial line if dx by d theta is equal to 0, where x is r cos theta or f of theta cos theta. And we can calculate the area of a closed region formed by the curve r equals f of theta and the rays or the half lines, theta equals alpha and theta equals beta, by evaluating the integral between alpha and beta of a half r squared d theta. So let's move and look at some examples. Our first example, we need to sketch the curve whose polar equation is r equals 1 plus 4 cos theta for values of theta between 0 and 2 pi, taking care to show the important features. Well, the first thing is we certainly know that the value of r cannot be more than 5 because cos theta lies between -1 and 1. So we've got the maximum value of r is 5 when theta equals 0. Now that tells me straight away that the whole curve must be inside a circle of radius 5, and what's more, that the point whose radius is 5 and whose angle is 0, which lies on the circle, is also on our curve. Now the minimum value of r, well, we know cos theta lies between 1 and -1, so the minimum value of r is -3. But we can't have a minimum value of r of -3 because r has to be at least 0. So that certainly tells us there are going to be some values of theta for which there are no values of r. It's worthwhile finding out when does r equal 0. Well, r equals 0 when 1 plus 4 cos theta equals 0. In other words, when cos theta equals -1/4. And if we're working in radians, cos theta equals -1/4 gives me theta is either 1.823 radians or 4.46 radians. So when theta equals 1.823 or 4.460, r equals 0 and the curve passes through the pole. That is the origin. What's more, it means that the rays or half lines, theta equals 1.823 and theta equals 4.46, are going to be tangents at the pole. So we'll dot those in as well. So there's theta equals 1.823, there's theta equals 4.46 radians. And for angles between 1.823 and 4.46, 1 plus 4 cos theta is going to be negative, so there aren't going to be any points on our curve. Finally, before we actually sketch our curve, we notice that r is in fact just a polynomial in cos theta, so the initial line is certainly going to be a line of symmetry of the curve. So putting all of that information together, we can get our curve C1. So notice that the curve C1 passes through the point r equals 5, theta equals 0. It passes through the pole. It's got the line, or the ray, theta equals 1.823 as a tangent to the pole, and also theta equals 4.46 is a tangent at the pole. And we've got the symmetry about the initial line. Now, the second thing we've got to do is we've got to find a Cartesian equation for this curve. Well, we know that r is 1 plus 4 cos theta, and we also know that we've got r is the square root of x squared plus y squared, x is r cos theta, and y is r sine theta. Now, if we're trying to move to the Cartesian equation, it's often a good idea to get rid of the angle first of all in the polar equation, and then to get rid of the radius. So the angle appears in the cos theta term, we can say that cos theta is the same thing as x divided by r. So the first thing we've got is r is the same thing as 1 plus 4x divided by r. We could multiply through by r to clear the fractions. So we've got r squared equals r plus 4x. We know that r squared is x squared plus y squared. We know that r is the square root of x squared plus y squared. So we've now got our first Cartesian form for the curve. We can tidy this up a little bit. If we pull the 4x across, so we get x squared plus y squared minus 4x equals the square root of x squared plus y squared, and then square each side, we've got x squared plus y squared minus 4x all squared has got to equal x squared plus y squared. And that would be a sensible way of leaving the Cartesian equation for the curve. Third part of this question shows us the curve C2, whose Cartesian equation is x squared plus y squared all cubed is equal to 16y to the 4. And we're asked to obtain the polar equation of C2. So there's the Cartesian equation, and again we've got the three things that we can use. We've got r as the square root of x squared plus y squared, x is r cos theta, and y is r sin theta. So straight away on the left hand side we notice that we've got x squared plus y squared all cubed. X squared plus y squared is just r squared, so the left hand side simplifies very quickly to r squared cubed. On the right hand side we can substitute y equals r sin theta and obtain r squared cubed equals 16 lots of r sin theta to the power 4. Simplify both sides, we've got r to the 6 equals 16 r to the 4 sin to the 4 theta. In other words, we've got r squared must equal 16 sin to the 4 theta. Which means that we've got r must be plus or minus 4 sine squared theta. But we know that r has got to be greater than or equal to 0. We know that sine squared theta certainly is positive or 0. So we can ignore the negative option. So we've got r is 4 sine squared theta. Moving on to the final part of this question, we wish to find the polar coordinates of the points of intersection of our two polar curves. So C1 had equation r equals 1 plus 4 cos theta, and we've just shown that C2 has got equation r equals 4 sine squared theta. We've got a picture of C2 all available, and there's the picture that we drew earlier on of the curve C1. We can see that both of these curves go through the pole. So first of all we do need to observe that the pole is one of the points of intersection of the two curves. To find the other points of intersection of the two curves, we need to solve the equation r1 equals r2, in other words 1 plus 4 cos theta equals 4 sine squared theta. Sine squared theta can be rewritten as 1 minus cos squared theta, and if we tidy that equation up, we're going to obtain the quadratic equation 4 cos squared theta plus 4 cos theta minus 3 equals 0. That has solutions of cos theta equals a half or minus 3 over 2. However, cos theta can plainly not be minus 3 over 2 because we know that cos theta always lies between minus 1 and 1. So we can rule that possibility out as being impossible. Cos theta equals a half gives me theta equals either pi by 3 or 5 pi by 3. If theta is pi by 3, then going back to either the equation for C1 or the equation for C2, we obtain r equals 3. And similarly, when theta equals 5 pi by 3, we obtain r equals 3. So we've got the points of intersection of the two curves are the point with polar coordinates 3 pi by 3, the point with polar coordinates 3, 5 pi by 3, and the pole. Moving on to a second example, we have the curve C has got polar equation r equals cos theta plus 2 sine theta for values of theta between 0 and pi by 2. We've got to find the polar coordinates of the point on C at which the tangent is perpendicular to the initial line. Now if the tangent is perpendicular to the initial line, then we have got the x by d theta must be equal to 0. X is equal to r cos theta. So x is cos theta plus 2 sine theta times by cos theta. So we can find dx by d theta by using the product rule. So first of all, differentiating cos theta plus 2 sine theta, we obtain minus sine theta plus 2 cos theta times by the cos theta left alone. And then adding on, we've got cos theta plus 2 sine theta left alone times by the derivative of cos theta, which is minus sine theta. If we simplify that, we've got dx by d theta is minus sine theta cos theta plus 2 cos squared theta minus cos theta sine theta minus 2 sine squared theta. So we've got two lots of cos squared theta minus sine squared theta minus 2 sine theta cos theta for the value of dx by d theta. Cos squared theta minus sine squared theta is cos 2 theta. 2 sine theta cos theta is sine 2 theta. So dx by d theta is the same thing as 2 cos 2 theta minus sine 2 theta. We want dx by d theta to equal 0, so that means we've got to have 2 cos 2 theta equals sine 2 theta. In other words, we've got tan 2 theta must equal 2. And if tan 2 theta equals 2, then I have got theta is 0.5536. But we still need to find the radius or the value of r at the point C. So if theta equals 0.5536, then we've got the value of r is cos theta plus 2 sine theta, which is 1.902. So the polar coordinates of the point C are r equals 1.902, theta equals 0.5536. For the second part of the question, we've got to find the area of the region enclosed between C, the initial line, that's the line theta equals 0, and the line theta equals pi by 2. So that we know that area is the integral of a half r squared d theta. So in this case, we've got a half times the integral between 0 and pi by 2 of cos theta plus 2 sine theta all squared. So if we expand the square, that gives me a half of the integral between 0 and pi by 2 of cos squared theta plus 4 sine theta cos theta plus 4 sine squared theta. And at this stage, if we remember that cos squared theta is the same thing as a half plus a half cos 2 theta, that sine squared theta is the same thing as a half minus a half cos 2 theta, and that 2 sine theta cos theta is the same thing as sine 2 theta, then we can rewrite the area integral as being a half of the integral of a half plus a half cos 2 theta instead of cos squared theta, 2 sine 2 theta instead of 4 sine theta cos theta, and 2 minus 2 sine theta instead of 4 sine squared theta. Tidying that up, we've got a half the integral between 0 and pi by 2 of 2.5 plus 2 sine 2 theta, take away 3 over 2 cos 2 theta. So if we integrate that now, we've got a half times 5 over 2 theta, take away cos 2 theta, take away 3/4 sine 2 theta, with limits of 0 and pi by 2. Putting the limits in, we obtain a half of 5 pi by 4 minus 1 minus 0, and then when we put the bottom limit in, we've got 0 take away 1 take away 0. So if we tidy that all up, we end up with 5 pi divided by 8 as the area we've been asked to calculate. And now let's have a look at a final example, which is a part question from 2008. So we've got diagram there shows part of the curve with polar equation r equals 1 minus theta. Point P is the point on C1 at which the tangent to C1 is parallel to the initial line. We've got to show that the theta coordinate of P satisfies the equation theta plus tan theta equals 1, and then later we've got an area calculation to do. So for the first part then, if the tangent is parallel to the initial line, then we must have dy by d theta equals 0, where y is r sine theta, which in this case is 1 minus theta times sine theta. So to find dy by d theta, we need to use the product rule. If I use the product rule, differentiate 1 minus theta, I get minus 1. Leave the sine theta alone, so the first term is just minus 1 times sine theta, plus, then I need to leave the 1 minus theta alone and differentiate the sine theta, which gives me 1 minus theta cos theta. So there's the result of using the product rule to find dy by d theta. We want dy by d theta to equal 0, which means that I've got to have 1 minus theta cos theta equaling sine theta, or in other words, if we divide through each side by cos theta, I must have 1 minus theta equals tan theta, which gives me immediately theta plus tan theta must equal 1. Moving to the second part of the question, we have to show that the area of the region enclosed by C1 and the initial line is 1/6. Well, notice that r equals 0 when theta equals 1. That means that the ray theta equals 1 is tangential at the pole. So the area that we're being asked for is the area underneath the curve, or the area formed by the curve and the rays theta equals 0 and theta equals 1. We know that the area is given by the integral of a half r squared d theta, so in this case it's just a half of the integral between 0 and 1 of 1 minus theta squared. And if we expand the square, then we obtain a half the integral of 1 minus 2 theta plus theta squared. And performing the integration, I obtain theta minus theta squared plus a third theta cubed. I need to put the limits in, so put theta equals 1 in and then subtract the value when theta equals 0. And we end up with just 1/6 as the question required.